binary frequency shift keying. So binary frequency shift keying or BFSK. BFSK in abbreviation form it is called BFSK, binary frequency shift keying. In binary frequency shift keying, the frequency of a sinusoidal carrier is shifted according to the binary symbol. We know in modulation technique some characteristics of carrier signal has been changed according to the baseband signal, according to the properties of baseband signal. Okay, so in BFSK, the frequency of sinusoidal carrier signal is shifted according to the binary symbol. In other words, the frequency of a sinusoidal carrier is shifted between two discrete values. However, the phase of the carrier is unaffected. This means that we have two different frequency signals according to binary symbols. Let there be a frequency shift by omega. Then we can write the equation for bit bt. When bt is equal to 1, then the high frequency signal that is represented by SHT, that will be equal to root 2 ps cos 2 pi fc. Fc is the basically carrier frequency, right? And it is shifted by omega, so fc plus omega into t. Okay, so this is for the symbol 1. Okay, in case of binary symbol there are two bits, namely 0 and 1. So for 1, when binary bit is 1, then the high frequency signal SHT will be equal to this, and when the bit is bt equal to 0, when the bit is 0, then the low frequency signal SLT will be equal to root 2 ps cos 2 pi fc minus omega, because here is also the frequency of the carrier signal is shifted by an amount of omega, right? So generation of BFSK signal, generation of BFSK signal, right? In the block diagram of generation of BFSK signal, there are two level shifter. Okay, so here is one level shifter, and the another one level shifter is here. Okay, so there are two level shifter and there is an inverter. So here is an inverter, right? Okay, so what is the function of this inverter? Inverter is basically invert the bit to the lower frequency signal from higher frequency signal. Okay, if this bit bt is basically the symbol that may be 0 or 1. Okay, if symbol is high, suppose the symbol is high here, so this generates basically a higher frequency signal that can be represented by pht. Okay, so the inverter inverts this higher frequency signal to these lower values. Okay, so this signal, the output of this inverter can be represented by PLT. So this is lower frequency signal basically. Now the gain of the level shifter is root over of PS into TB. Okay, so the output of this level shifter will be root over of PS TB into PH T. Okay, so this is the higher frequency signal. So this is the output of this level shifter, and the output of this level shifter will be gain into, gain is multiplied by the input So input is here PLT, so this will be root PSTB into PLT. Okay, now there is a mixer here. Okay, and here is also a mixer to mix the carrier signal. Okay, now what is the carrier signal for higher frequency signal? Suppose the carrier signal is 51T equal to root 2 by TB. Okay, this is basically bit duration. TB is basically bit duration. Okay, into cos 2 pi FHT. So this is the high frequency FHT, right? And for this mixer, the carrier signal will be phi 2T equal to root over of 2 by TB cos 2 pi FLT. Okay, so after this mixing, both the signals will be added to an adder, right? So both the signals will be added here, and we get the BFSK output signal. So BFSK signal as the output, right? So this is the block diagram of a BFSK signal generation, right? Now in the receiver section, now what will be the output of this BFSK signal? That will be ST will be equal to root over of 2 PS into PHT, this portion. Okay, actually both the portion will be multiplied. Okay, so cos 2 pi F H T. Okay, and plus this portion will be added. So here will be 2 PS into PLT cos 2 pi FL into T. So this is the output of this block diagram basically, or this is the BFSK modulated output. Okay, now what will be the pass spectral density? So spectrum of BFSK, what will be that the pass spectral density of BFSK signal is basically SF will be equal to root over of PS by 2. This is unit impulse function, so delta of F minus FH, okay, plus delta of F plus FL. This is higher frequency and this is the lower frequency, plus PSTB by 2 sin pi FH TB by pi FH TB whole square plus PSTB by 2 sin pi FL TB by pi FL TB. So this is basically sinc function, right? So whole square, this portion. So this is the pass spectral density of BFSK signal. Okay, now the spectrum of BFSK signal looks like this. So the spectrum of BFSK signal will look like this. Okay, so originally the signal is basically if the amplitude of this signal, original signal, is this, so it looks like this way. Okay. So signal will look like this. Okay, so here is the lower frequency FL. This is lower frequency FL, and this is the upper half frequency or high frequency FH. Okay, and this is the frequency for transmitting 1 bit, so this is FB, right? So this is also FB. So what will be the bandwidth? That will be FH. Bandwidth will be equal to FH minus FL, right? That will be equal to 2 FB. So this will be the bandwidth part. Now BFSK detection. So BFSK detection or BFSK receiver, right? So receiver section. Now the block diagram of BFSK detection is this. There will be a mixer here, okay, and there will be a integrator circuit. Now integrating from 0 to TB dt, right? Here is also another integrator TB0, this is dt. There is also another integrator here, and here is also another mixer. Okay. We know in the demodulation section we generate locally carrier signals. We generate carrier signals locally. Okay, so here will be cos 2 pi f c2 into t, and this will be cos 2 pi f c1 into t, right? And the output of this mixer will goes to an integrated circuit, right? And here the binary FSK or BFSK wave. So this is basically BFSK wave. Okay, so BFSK wave actually goes to this mixer, and these are the carrier frequencies. This is basically high carrier frequency, and this is low carrier frequency. The output of the mixers goes to the integrator 1 and integrator 2, and both the output, suppose this output is L1 and this output is L2, so both the output basically goes to a comparator to compare both the signals, right? So here is a comparator, and the output L1 goes here, sorry, L1, this is L1, right? And output L2 is also here. Okay, now here the comparator checks the symbol whether this L1 greater than L2 or L1 less than L2. If L1 greater than L2, so if L1 greater than L2, right, if L1 greater than L2, then the symbol will be 1. Okay, for L1 symbol will be 1. If L1 less than L2, then the symbol, so else the symbol will be 0, right? So this will be the output. Okay, so block diagram of demodulation BFSK wave using coherent detection technique consists of two correlators. This basically this section is called correlator. So this is correlator 1, and this section is correlator 2, right? So there are two correlators that are individually tuned to two different carrier frequencies to represent symbols 1 and 0. A correlator consists of a multiplier followed by an integrator. the received binary FSK signal is applied to the multiplier followed by an integrator. Then the received binary FSK signal is applied to the multipliers of both the correlators. To the other input of the multipliers, carriers with frequency FC1 and FC2 are applied as shown in figure. The multiplied output of each multiplier is subsequently passed through the integrator in generating L1 and L2 outputs. Okay.